Hello everyone, myself Raki, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Optical Communication, I am going to deliver before you Power Penalties and Introduction to Multi-Channel System. So before going detail towards the topic, let's have a brief introduction of the topic which I will cover today. First, I will give you the brief description about the power penalties and the different types of power penalties which are mentioned here. This all are the different types of penalties, power penalty, and then at last I will give a brief introduction to the multi-channel system. So, before proceeding forward, just have an introduction of the power penalties. Whenever a penalty come into our mind, the first thing which we come into it is that penalty means something wrong which we have to compensate. So same thing happens for this is also power penalties. If some wrong and something misalignment or some loss or some impairment occurs in the case of a power transmission in the optical communication, that comes under the category of power penalties, and we have at last do something either in the distribution system, either in the transmission system, either at the receiver or the transmitter section, so as to reduce this power penalty. So a number of signal impairment or damage are natural in optical fiber transmission system, and this can degrade the link performance. Here we are talking about the digital optical power link, and when any of this impairment are present in the link, this will lead to the reduction in the signal to noise ratio. So just have a recap of the signal to noise ratio. Signal SNR, it is given by the term SNR, and it is the signal received upon the noise received. And of course, as this shows signal upon noise, so in any receiver section we want the maximum strength of the signal as compared to the noise. So its value has to be greater side at the receiver section, and if any misalignment or impairment or any damage occurs to this SNR ratio, that means we are getting noise as compared to noise is much more as compared to signal, and in that case our SNR ratio will decrease. That's why when any of this impairment, the impairment which is caused by any of the factors which occurs in the optical communication present in the link, there is a reduction in the SNR, and reduction in the SNR is known as the power penalty. For that effect, and generally it is expressed in decibel. Already we have discussed previously number of times that whenever powers are represented in the form of a ratio, at last it is represented in the form of a decibels. So power penalties is then given as ppx is actually our power penalty minus 10 log SNR impaired, SNR which is due to the impairment in our link, optical link, and SNR at the ideal condition. The ratio between these two, and when it is taken the log of that, we will get the power penalty. So now SNR impair is the SNR at the impair or damaged condition of the optical power link, and SNR ideal is the SNR at the ideal condition when there is no damage or impairment etc. in the optical link. And if we want to reduce the power penalty, of course we have to increase the strength of the power at the optical receiver section. The main power penalties are chromatic dispersion penalties, polarization mode dispersion penalty, which is also represented as PMD, extension penalty, modal noise, mode partition noise, chirping, and the at last reflection noise. These are the different types of impairment or the damage which occurs in the case of a optical power link. Now first one, the chromatic dispersion penalty. So whenever the dispersion term comes to your context, what is the first thing which comes to our mind? That dispersion is a process. Already it is discussed in the unit 2 when we are talking about the noises in the transmission system of an optical communication. Dispersion means basically broadening of the signal. Broadening of the signal, whenever we say that broadening of the signal, that means our signal is impaired. Or damaged. It is not in the original condition as it is. And now the chromatic. Already in the dispersion section we have studied about the different types of the dispersion. One of that is the intramodal and the another one is the intermodal dispersion. So chromatic dispersion is basically our intramodal dispersion. About that which we have already studied. So the whatever is the cause of the chromatic dispersion in the case of optical fiber or transmission medium of the optical communication, same is the reason behind the chromatic dispersion penalty, because both are providing the impairment or damage to the signal which is transmitting within the optical communication. So chromatic dispersion originates from each wavelength if travel at slightly different velocity in a fiber, and thus they arrive at different times at the fiber end. What this statement says that if in a multi-mode fiber, number of signals are traveling having a different velocity, and if they are traveling at a different velocity, obviously they will reach at the destination end at the different time, and this will lead to the chromatic dispersion. Chromatic dispersion is a fixed quantity at a specific wavelength, and its unit is picosecond per nanometer kilometer. The accumulated chromatic dispersion increases with the distance along a link. What does this say? That if the distance between the source and the destination increases, that is, if the length of the optical fiber increases, of course the chromatic dispersion increases along with it. That means it's the chromatic dispersion penalty is directly proportional to the length of the fiber, because also the chromatic dispersion occurs in the optical fiber. Therefore, either a transmission system has to be designed to tolerate the total dispersion, or some type of dispersion compensation method has to be employed. So, if we want to reduce this chromatic dispersion penalty, either we have to design a system which can tolerate the dispersion which is occurring, or other if we can't design the system which can able to tolerate the dispersion, we have to of course design a compensation method which will of course reduce the penalties which is occurring due to this chromatic dispersion. Now the second one, the polarization mode dispersion penalty. So polarization mode, already we have discussed in the noise section. This polarization mode dispersion penalty is also due to the fiber, optical fiber, which is our transmitting medium. So this type of penalty arises in the optical communication in the transmitting section. And how it arises? When the light signal energy for a given wavelength in a single mode fiber occupies two orthogonal polarization states or mode. It arises when a light signal occupies two orthogonal states or modes of a optical communication. Already we have discussed the different types of mode which occurs in the case of optical communication: EH, HE, TM, TE. All these are the different types of modes which occurs in the case of optical. So if two orthogonal modes arises, then that will lead to the polarization, mode dispersion, penalty. PMD arises because the two fundamental orthogonal polarization modes travel at slightly different speed owing to fiber birefringence. So two orthogonal modes travel at different speed, and this will lead to the dispersion penalty. That is, the resulting difference in the propagation times between the two orthogonal mode polarization will result in a pulse spreading. Pulse spreading is the basic phenomenon of the dispersion. And so again the thing comes that how can we reduce the PMD? So PMD does not fluctuate widely for cables that are enclosed in the underground duct or in a building. However, it can increase periodically to over 1 picosecond per under root of kilometer for outside cables, because that clearly indicates that underground cables have a lower exposure to polarization mode penalty as compared to the outside cable that are suspended on poles, etc. Since each cable are subject to wide variation in temperature, wind induced stresses and elongation caused by ice loading. So what the final interpretation? If we want to reduce the PMD, we have to design such a system, such a cable that are underground or inside the building, because the outside cables that are suspended on the poles get exposure to temperature, wind, stresses or any other environmental factors that will increase the polarization mode dispersion penalty. Now comes the extension penalty. So extension penalty basically is a ratio of now first penalty which we have studied, that is the chromatic dispersion and the polarization modes penalty, are basically the penalty arises due to the optical fiber which is our transmitting medium. So here we are come across the different type of penalty which arises, some arises due to the source, some arises due to the receiver section and some arises due to the transmitting section. The first one arises due to the transmitting medium and this one is due to the source. The extension ratio which is represented by R underscore E in a laser. So we can easily say that this penalty is caused by the source. Is defined as the ratio of the optical power level P1 for a logic 1 to the power level 0 for a logic 0. That means here we have come across the two conditions, when the power is inside is given and when the power is not given. That's why it is called the extension penalty. Extension means, already we have in general layman terms, we can say extension means completely end of that. So this penalty arises when signal is coming and when signal is not coming. If we want to depict when the signal is coming and when the signal is not coming, we have to go through this penalty value. Then we will able to say up to what value the signal is available and when the signal is not available. Easily we can say that if the RE value is greater, in that case we can say that at the signal 0 condition, that means non-availability of signal from the laser source is less. But when RE is less, what does it mean? That non-availability of signal from the laser should be on the greater side. So we are able to judge whether the signal is coming at what rate and in what proportion from the source by seeing this extension penalty ratio. Ideally, the extension penalty ratio have to be infinite, because ideally we always used to say that the source capability of giving the signals or the flow of signal from the source should not be interrupted. It should be in a regular fashion or in a continuous manner. In that case, no condition of power level 0 will occur, and if always there is a power 1 is available, that means flow of power is going on. So anything divided by 0, result is infinity. Though in ideal condition, when we are assuming that power coming from the source is not interrupted in any case, in that case we have a extension ratio to be a infinite. So there will be no power penalty from this condition. Of course, when the extension ratio is infinite, there is no power penalty from this particular source, the laser, which is providing the signal. The extension ratio, but actually what has happened? Extension ratio is finite in an actual system in order to reduce the rise time of laser pulse. So here it is a power penalty versus extension ratio graph. We are able to see that here it is extension ratio value, and when the extension ratio values increases, power penalty increases proportionally. Now comes the modal noise. This type of modal noise comes into existence when we are talking about a multi-mode system, where number of modes are operating inside a single fiber. So in multi-mode, whenever someone asks me about the modal noise, so first thing, without any hesitation, if we are not able to say anything, modal noise comes from the multi-mode system. And already you know that multi-mode fiber is that type of fiber when number of modes are traveling inside a fiber. And when the number of modes are traveling inside a fiber, of course there will be some interference between that different types of modes which are inside the fiber, and the noise which are generated due to this interference is the modal noise. Of course, this will of course interfere with the power signal which is flowing inside the fiber, and this ultimately leads to the power penalty. So without knowing anything detail, you can easily able to say something about anything by simply looking at this name, because you have already studied many things about this modes and optical fiber multimode. In multimode fiber, there is an interference among various propagating modes, which results in fluctuations in the received power. The same line is written here also, but the words which are used are different. This fluctuation are called as the modal noise, and modal noise is more serious with semiconductor laser. When light from coherent laser is launched into the multimode fiber, a number of propagating modes are excited. So when the light from a coherent source laser is launched, a number of propagating modes get excited. As long as this mode retain their relative phase coherence, that means they remain in the same phase, coherence phase maintaining, that it will remain in the phase which is assigned to it. The radiation pattern seen at the end of the fiber takes on the form of a speckle pattern. This is a speckle pattern, and each speckle which is shown here represent the propagating mode. Represent the propagating mode. Each speckle, this is a different type of structure which is shown here, is basically the speckle, and each speckle represent the different types of propagating modes. And here it is a laser which is emitting the light and propagating here. So there, of course, when the number of modes are traveling, they form a constructive interference or the destructive interference which will occur. A number of speckles in the pattern approximate the number of propagating mode. Now the mode partition noise. So mode partition noise is associated with the intensity fluctuation in the longitudinal modes of a multi-mode laser diode. So this mode partition noise exists due to intensity fluctuation in the longitudinal modes of a multi-mode laser diode. So we can say that this noise is also very much prominent in the case of a multi-mode system. In this case, what is happening? The side modes are not sufficiently suppressed. So if there is a single mode we want to have, and if the side modes are also in less intensity, that's why one mode is said to be prominent. So if we want to achieve this particular mode, we have to suppress this side lobes, and if these side lobes are not properly suppressed or not properly minimized to the zero level, of course it will lead to the noise. In multi-mode fiber, various longitudinal modes fluctuate even though intensity remains constant. This mode creates, so of course in a longitudinal one is functional, but many other are also functional in a small quantity, but it is functional. That's what is called as a side one. So this will lead to the mode partition noise. As a result, all modes are unsynchronized and creates additional fluctuation, and in turn it will reduce SNR, and if it will reduce the SNR, it will lead to the power panel. This is the expression for the mode partition noise. Now the second one is this one is the chirping. Chirping is basically a change in the carrier frequency due to change in the refractive index. Already we have come across that refractive index very severely affects the propagation in the optical fiber. So whenever change in the carrier frequency due to change in the refractive index, then that is called the frequency chirping. Because of the frequency chirping, what is happening? The spectrum of the optical pulse get broadened, and of course at the end it will degrade the system performance. We can able to see this. This is a signal without the chirp, frequency chirping. So of course the broadening is less or negligible, we can say, we can call it the less, but here is a optical input pulse with a chirp. You can easily say that the broadening is much more in this case. And what is the final consequence of this broadening? Dispersion, and dispersion of course led to power penalty. Now the last of the power penalty, that is the reflection noise. When the light travels through a fiber link, some optical power get reflected at the refractive index discontinuities, because when the light travels inside the fiber, the refractive index discontinuities occurs in the case of core and cladding, because already we have known that core and cladding have a different refractive index, and due to this difference in the refractive index, the total internal reflection, which is the main reason behind the propagation of light inside the optical power, works. And also there occurs some splices, couplers and filters in the propagation system, and this will also lead to refractive index discontinuity, because their refractive index will be different from the fiber refractive index. The reflected signal can degrade both transmitter and receiver performance since they reduce the SNR. This effect causes two types of power penalty in the receiver sensitivities. What are these two? First, multiple reflection points setup and interferometric cavity that feeds power the laser. Because what is the reflection system do? Because incident then transmitted and reflected, that is just going back to the source. So what will it do? It led to the interferometric cavity that feeds the power back to the laser cavity, which is basically the source of the incident signal. The second effect created by the multiple optical path. Of course, this is the path and the reflected signal are creating another path. Is the appearance of spurious signal arriving at the receiver with variable delay, therefore causing intersymbol interference. Intersymbol interference already we have come across, which arises due to the another signal which is coming, and it will lead to the intersymbol interference, which is also called as the eyesight. And this all are due to the reflected signal which are coming towards due to discontinuities in the refractive index. Either there is no discontinuity, in that case the reflection of a signal, it will be 0 in the ideal case, when there is no discontinuity in the refractive index. Now, just introduction to the multi-channel system. Development of a new multi-channel system. Why it is done? In order to exploit the enormous capacity provided by the optical medium, so as to achieve maximum from the optical system, optical fiber system. This multi-channel system are designed. Some of these are: first, electronic multiplex. The medium is the optical medium, ETDM, electronic time division domain multiplexing. Then SCM, subcarrier division multiplexing, which is the basically frequency division multiplexing. Then optical multiplexing. The first one is the OTDM, optical time division multiplexing, and WDM, wavelength division multiplexing. So about these different types of multiplexing techniques which are designed for so to get the maximum from the optical system, we will discuss in the next class. Thank you for attending today's class.